Hi everybody. In the last video we saw some basic examples of trigonometric equations and how to solve them. One of the main things that you learned is how to come up with a general solution once you've gotten a single solution to your equation. So we're going to continue to use that, but we're going to add in some new strategies. We're going to talk about how to use factoring and how to use taking square roots in order to solve equations that have squared terms in them. So in this example, my first goal, in any of the examples, I'm going to first want to get the trig function by itself. So get trig function. In this case, that's tan of x by itself. So I use the basic strategies that I would when solving any equation. So first I bring the 1 over, so I'll have 3 tan squared x equals 1. Then I'll divide by 3. And now I almost have tan squared tan by itself, but I need to take a square root in order to finish that process. So here, maybe let's actually call this 1a because it's still part of that last step. Take square root of both sides. That's how you get rid of a squared, unless you can factor. In this case, we can't really factor. So if I take the square root of both sides of this, then I get tan of x equals the square root of 1 over the square root of 3, which is the same as 1 over the square root of 3. And an important thing here is that whenever I take a square root, I have to use plus or minus. So now what I need to do is get x. So find x. And my strategies for doing that are just like in the last video. So I'm going to use a triangle or inverse trig function. This will help me get my solution in quadrant 1. And after that, I'll need to get my general solution by using the fact that trig functions are periodic. Periodicity is the word that means it is periodic. Okay, so let's work on this step, using a triangle to get at least one solution. So I'll draw a triangle, a right triangle, and I can choose x to be one of the remaining two angles. Tan is opposite over adjacent, so I label the opposite as 1 and the adjacent as root 3. You might recognize that this is a special triangle. It's the 30, 60, 90. The 30 is opposite the 1. This side would be 2, so I know that x equals pi over 6 is my solution in quadrant 1. Now, I can recognize that when tan is positive, I could either be in quadrant 1 or quadrant 3. But I also have negative solutions, so I could have an answer in quadrant 2 and quadrant 4. So my answer in quadrant 2 is going to be pi over 6 less than pi. So it will be pi minus pi over 6, which equals 5 pi over 6. And my solution in quadrant 3 would be pi plus pi over 6, which is 7 pi over 6. And my solution in quadrant 4, so that was in Q1, this was in Q2, this is in Q3. My solution in Q4 is going to be 2 pi minus pi over 6, which is 11 pi over 6. So my general solution is going to be pi over 6 plus pi times k and 5 pi over 6 plus pi times k. Usually we have a 2 pi here rather than pi times k, But notice that if you add pi to pi over 6, you get 7 pi over 6. So this encompasses both of these solutions. And this encompasses both of these if I use pi rather than 2 pi. If I used 2 pi, I'd skip this one and I'd have to have 4 different things here with pi over 6 plus 2 pi k, 5 pi over 6 plus 2 pi k, 7 pi over 6 plus 2 pi k, etc. So let's do another example where taking square roots will not work, one where we really truly need to use factoring. So here's the example that I want to look at. The reason that we know that we need to use factoring is because I have both squared terms and not squared terms. So we use factoring when we have both squared terms and not squared terms. So in order to factor this, I'll first bring the cotan over. So I have cotan x, cosine squared x, minus 2 cotan x equals 0. In order to factor, I always need to have it equal to 0 on one side. So now, to factor, I'm going to pull out a common factor. There's a cotan in each of these terms. So if I pull the cotan of x out, then from the first term, I'll be left with cos squared x, and from the second, I'll be left with minus 2, and this equals 0. So now I use my strategies for solving equations that are factored. If I have two things which multiply to 0, that means that either the first one is 0, or the second one is 0. So let's deal with this one first. If cotan of x equals 0, well, remember that cotan is cosine of x over sine of x. So this means that cosine of x has to equal 0. So if I go to my unit circle, cosine of x equals 0 whenever the x coordinate is 0. So I get this solution and this solution. So pi over 2 and 3 pi over 2. This function is 2 pi periodic, so I get my general solution by adding on multiples of 2 pi to each of these. Okay, so that gives us one set of solutions. To get the other set, I don't need to factor anymore because I have a squared term, but I don't have a non-squared cosine term. So the strategy I'll use here is like in the last example. I'll take a square root. So I have cosine squared equals 2, which means that cosine x equals plus or minus the square root of 2. Now, this does not come from any special triangle, so I might use my calculator to solve it. So I need to find x is going to be the inverse cosine of square root of 2 to give me my solution in quadrant 1. So if I do inverse cosine square root of 2, then what happens, maybe you can already predict this, I get an error. Now why is that? So there's no solution. The reason is that the square root of 2 is 1.414, blah, 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 blah. This is bigger than 1, and so there is no angle whose cosine is bigger than 1. So this doesn't give us any solutions. So we can't actually solve this equation for that reason. Okay, so I have one more example for you. 2 sine squared x minus sine x minus 1 equals 0. So in order to solve this one, I know that I need to use factoring because I have a squared term and a non-squared term for sine. So let's factor. And then after I factor, I'll get a solution. We're just looking for solutions in the interval from 0 to 2 pi. So we don't need a general solution. So to factor this, I'm going to separate it into two terms, and that's going to equal 0. This term times this term better multiply to 2 sine squared x. So the only way I can do that is if I put 2 sine x on one and sine x on the other. This term and this term have to multiply to minus 1, but when I do the outer and the inner together, that has to add to minus sine x. So the way that I'll do that is I know it's going to have to be a 1 and a 1. When I do the outer, this is going to give me 2 sine x. When I do the inner, that gives me sine x. When I add 2 sine x to sine x, that gives me 3 sine x unless I make this a minus, which would give me negative 2 sine x plus sine x, which gives me the minus sine x that I'm looking for in the middle here. So now that I've factored, I have two new equations. So I have 2 sine x plus 1 equals 0, or sine x minus 1 equals 0. And I'll just solve these using my basic strategies. So I'm trying to get sine x by itself. So 2 sine x is minus 1. And so sine x equals minus a half. So now I need to find x. Let's get a solution in quadrant 1. To do that, we'll use a special triangle and assume that we had positive 1/2. So x opposite over hypotenuse. Again, this is the 30, 60, 90. So in quadrant 1, we'd have x equals pi over 6 as our solution. That's the angle whose sine is 1/2. But we're looking for the angle whose sine is negative 1/2. So our true solution is in quadrant 3 and quadrant 4. So I have to go pi over 6 in this direction and pi over 6 in this direction. So my true solution is going to be pi plus pi over 6, which is 7 pi over 6. That's this one. And then 2 pi minus pi over 6, which is 11 pi over 6. That's this one. Okay, now let's solve the other equation. Here I have sine of x equals to 1. So I need to figure out what angle gives me sine equal to 1. This one's actually a little bit easier because sine is the y coordinate on the unit circle. So when is that equal to 1? Well, only right there. Here it's 0, here it's negative 1, here it's 0. So from this, I get that x equals pi over 2. So these are my three solutions. And there you have it. That's how we use factoring to solve equations where one of the trig function terms is squared. Also, just to note, it's not necessary that one of the trig functions is squared. For example, we could factor if we had an equation like this. I could still pull out the cotan x, and then I'd be left with sine x plus 1 equals 0. So it's not a hard and fast rule that you should only factor if you see a squared. You should factor when it looks like you can factor. If you have terms that share a common factor, then you should factor it. We're always trying to make things simpler. And generally we can solve equations better if we have it in factored form, because then we get two more simple equations that we can solve. So I hope that this is helpful. We'll do a lot of practice in class, and I will see you soon.